Hey everyone, welcome to this explainer. Today, we're diving straight into a massive, almost magical mystery. How exactly does AI process complex visual data without just completely crashing? Every single day, we feed AI millions of high-res photos, and it instantly recognizes cats, dogs, cars, faces, you name it. But mathematically, that is an overwhelming mountain of data. So, let's uncover the incredibly elegant trick that makes modern computer vision actually work.
So, this brings us to the central detective question we need to answer today. Can we simplify the network by just relying on the inherent properties of the images themselves? Think of this as our search for a mathematical cheat code. Because if we treat an image like a massive random grid of numbers, our AI just drowns in data. But if images have predictable rules, well, we can build a much smarter, leaner machine.
Think about a vibrant, detailed picture of a bird. To you and me, it's just a single object, right? But to a computer, it's literally millions of individual pixels. In a traditional neural network, the AI tries to connect every single pixel to every single neuron, all at exactly the same time. It's kind of like trying to memorize an entire forest just to understand what a leaf is. It takes massive computing power, and frankly, it's wildly inefficient.
Okay, here's our roadmap for today. We're going to hit the image processing problem, then the 3 rules of images, move into the convolution step, look at shrinking data with max pooling, and finally, put the whole shebang together in the full CNN pipeline.
Let's jump right into part 1, the image processing problem and the 3 rules of images.
All right, rule number 1. Some patterns are much smaller than the whole image. I mean, think about it. You don't need to see the entire picture to recognize a specific part of it. If you're looking for a bird, you just look for a beak, right? Or some feathers or a claw. AI can do exactly the same thing.
For instance, we can create what we call a beak detector. A single neuron in our network doesn't have to care about the sky or the tree branch or the tail just to find that one beak. By connecting only to a tiny, localized region of the image, we drastically cut down the math the network actually has to do.
Which naturally brings us to rule number 2. The exact same patterns appear in different regions. A beak is still a beak, whether the bird is perched way up in the top left corner or sitting dead center. Its core visual characteristics don't change just because its GPS coordinates on the screen moved.
And because of this rule, our network doesn't need to relearn what a beak looks like for every possible location. We can use the exact same detector, literally the exact same set of parameters, to find the beak in the upper left or the middle. Reusing these parameters saves a massive amount of processing power. It's a real game changer. Finally, we have rule number 3. Subsampling pixels won't change the object. Basically, if you take a high-def photo of a bird and kind of zoom out or shrink it down, it doesn't suddenly magically turn into a dog. The core identity of the image remains perfectly intact even if we toss out some of the raw pixel data.
By subsampling, we're basically making the overall image smaller and just dropping redundant details. The absolute crucial takeaway here? Fewer pixels means significantly fewer parameters to process. Yet, our AI can still clearly identify that it's a bird. It is an incredible shortcut. Next up on the agenda, the convolution step. Let's look at how the machine actually uses these rules.
So the engine driving this whole network is something called a filter. You can picture a filter as a sort of mathematical magnifying glass. It's just a small matrix of parameters that actively scans over the image, specifically looking for small localized patterns, like that beak we were just talking about.
Let's peek at the math behind the magic for a second. Imagine our image is a simple 6x6 grid of numbers. Right next to it are our filters, these smaller 3x3 grids that hold the actual parameters the AI is learning. Filter 1 might be looking exclusively for diagonal lines, while filter 2 is searching for vertical edges. Each filter is basically a dedicated detective. Now watch how this builds in motion. That 3x3 filter physically slides across the larger image, step by step. We actually call that step a stride. As it slides, it calculates a score for every single region, scanning the entire grid to see if its specific pattern exists anywhere at all.
The efficiency gained here is absolutely staggering. In a heavy, traditional network, parameters explode because everything has to connect to everything. But here, by looking only at small regions and sliding those same shared weights across the image, we use a tiny fraction of the parameters. It's just a way smarter, faster analysis.
Moving on to shrinking with max pooling. This is where we aggressively apply that 3rd rule of images.
Max pooling is essentially an ultra-aggressive data compressor. It subsamples the pixels from the convolution step, keeping only the absolute strongest signals, literally the maximum values in a given region. This creates a much smaller image while keeping the core object perfectly intact. We just strip away the noise, and then repeat this for every single filter channel.
All right, finally, the full CNN pipeline. We have all the puzzle pieces now, so let's look at the assembly line as a whole.
Just look at how beautifully this all loops together. A raw image enters, and we hit it with convolution, our magnifying glasses. Then, max pooling shrinks it down. We take that new, smaller image and run it through convolution again to find deeper patterns, and then shrink it again. This loop extracts incredibly rich features while totally managing the data size.
So to quickly summarize, we detect local patterns with convolution, then subsample and shrink with max pooling. After repeating those steps a few times, the data's tiny but packed with filtered features. We then flatten it out, literally unrolling it into a one-dimensional line, and feed it into a traditional network to make the final decision.
To really put this into perspective for you, after starting with a massive image and running it through 2 layers of this process, the network might shrink all that visual data down to a flat sequence of just 1,250 values. Think about that. 1,250 numbers is all the final network needs to understand the image perfectly.
That's the true genius of the convolutional neural network. It's not that it calculates everything, it's that it calculates exactly what it needs to. By mimicking human visual logic, finding small parts, reusing detectors, and zooming out without losing context, the AI does immensely more with significantly fewer parameters.
So I'll leave you with this thought. In the early layers, these simple matrices are just looking for edges, or maybe a tiny bird beak. But as you stack these convolutions, simple lines combine into shapes, shapes into objects, and objects into complex concepts. If simple math filters can detect a beak, what incredibly rich, complex features could these networks build to understand the rest of our world? Thanks for joining me on this explainer. It's been a blast.